12.1 Analysis Model. Rigid object in equilibrium. The outline of this video is as follows. We will begin by expanding our understanding of equilibrium from simple particles to extended rigid bodies. This requires introducing the two fundamental conditions that must be satisfied. We will define the first condition as translational equilibrium, which relates to the net force, and the second as rotational equilibrium, which relates to the net torque. Then, we will focus on the important special case of static equilibrium, where an object is completely at rest. To make problem solving more practical, we will then explore how to apply these principles in two-dimensional situations involving coplanar forces. Finally, we will summarize these concepts into a cohesive analysis model for rigid objects in equilibrium. We will now expand our understanding of equilibrium from simple point particles to more realistic, extended objects. Previously, we defined equilibrium for a particle as the state where the net force is zero, resulting in constant velocity. But real-world objects have size and can rotate, so this condition is not enough. For example, if you push on opposite ends of a pencil with equal but opposing forces, the net force is zero, but the pencil will spin. This shows that an object can have zero net force and still not be in complete equilibrium because its rotational motion is changing. To account for this, we must introduce a second condition. This condition involves torque, which is the rotational equivalent of force. Torque is what causes an object to change its rate of spin. So, to fully describe equilibrium for an extended object, we must consider both the forces and the torques acting on it. To understand the equilibrium of an extended object, we must consider torque, which is the rotational equivalent of force. Just as a net force causes an object to accelerate linearly, a net torque causes an object's rotation to speed up or slow down. This change in rotational speed is called angular accelerations. We define torque, represented by the Greek letter tau, as the cross product of the position vector r and the force vector F. The vector r points from the axis of rotation to where the force is applied. The rotational version of Newton's second law is that the net torque equals the moment of inertia I times the angular acceleration alpha. This leads us to the condition for rotational equilibrium. An object is in rotational equilibrium if its angular acceleration is zero. This means its rotational speed is constant, which could be zero or a non-zero value. For example, a spinning flywheel with no friction is in rotational equilibrium. Therefore, the essential condition for rotational equilibrium is that the net torque acting on the object about any axis must be zero. To fully describe the equilibrium of a rigid, extended object, we must satisfy two distinct conditions simultaneously. These conditions address both how the object moves through space and how it rotates. The first condition is for translational equilibrium. This states that the vector sum of all external forces acting on the object must equal zero. As a result, the acceleration of the object's center of mass is zero, meaning it moves with a constant velocity. The second condition is for rotational equilibrium. This requires that the vector sum of all external torques acting on the object calculated about any axis must also be zero. This ensures that the object's angular acceleration is zero, so it rotates with a constant angular velocity. For example, a perfectly balanced seesaw is in equilibrium because the upward force from the pivot cancels the downward weights, and the torques from each side cancel each other out. These two requirements, zero net force and zero net torque, together define our analysis model, which we call the rigid object in equilibrium model. Now let us focus on a very important special case called static equilibrium. We have already established that for an object to be in equilibrium, the net force and net torque acting on it must both be zero. This ensures that its translational and angular accelerations are zero. Static equilibrium adds a further, more restrictive condition. The object must be completely at rest relative to the observer. This means the object has no motion whatsoever. The translational velocity of its center of mass is zero, and its angular velocity is also zero. Think of a bridge supporting traffic, or the frame of a skyscraper. These structures are designed to be in static equilibrium, remaining stationary under the various forces they experience. This concept is fundamental to many fields of engineering. So the key takeaway is that for an object in static equilibrium, both its acceleration and its velocity must be zero. Let us pause to address a common pitfall regarding the condition of zero net torque. It is easy to mistakenly assume that if the net torque on an object is zero, then the object cannot be rotating. This is not correct. According to the rotational form of Newton's second law, net torque causes angular acceleration. Therefore, a net torque of zero simply means that the object's angular acceleration is zero. This leaves two possibilities. The object is not rotating, or it is rotating at a constant angular velocity. This is perfectly analogous to the translational case we studied earlier. A zero net force means constant velocity, not necessarily zero velocity. An object can be moving at a steady speed in a straight line with no net force on it. So the key takeaway is that an object in rotational equilibrium can still be rotating, as long as it does so at a constant rate. Let us examine a special arrangement of forces called a couple, which clearly illustrates why we need two separate conditions for full equilibrium. A couple consists of two forces that have the same magnitude and are pointed in opposite directions, but they act along different, parallel lines. If you add these two force vectors, they cancel out, resulting in a net force of zero. This means the object is in translational equilibrium and its center of mass will not accelerate. However, because the forces do not act through the same point, they work together to create a turning effect. This results in a non-zero net torque, so the object is not in rotational equilibrium. For example, when you turn a steering wheel with two hands, you are applying a couple. The wheel rotates in place but does not move forward or backward due to your hands. A couple produces a pure rotation without any translation. Now, let us simplify our equilibrium conditions for a very common scenario, when all forces act within a single two-dimensional plane. When forces are coplanar, meaning they all lie in the xy plane, our two vector equations for equilibrium become three more manageable scalar equations. First, the sum of all force components along the x-axis must be zero. Second, the sum of all force components along the y-axis must also be zero. These two equations ensure the object has no translational accelerations. The third condition is that the sum of all torques about an axis perpendicular to that plane, which we can call the z-axis, must be zero. This handles rotational equilibrium. The most important strategic insight here is that you can choose any point to be the axis for your torque calculation. This freedom is a powerful tool. For example, if you place your axis at the point where an unknown force is applied, that force's moment arm is zero, its torque is zero, and it vanishes from the equation, simplifying the algebra. For 2D equilibrium problems, using these three scalar equations and a clever choice of axis is the key to an efficient solution. This slide formalizes the analysis model for a rigid object in equilibrium, which is essential for understanding any structure that is stable and not rotating. For an extended object to be in equilibrium, two distinct conditions must be satisfied. First, the object cannot have any translational acceleration, which means its center of mass is not speeding up, slowing down, or changing direction. This state of translational equilibrium occurs when the net external force on the object is zero. This is the same condition we used for particles. Second, the object cannot have any angular acceleration, This state of rotational equilibrium occurs when the net external torque about any axis is zero. Forgetting this second condition is a common mistake when moving from particle mechanics to rigid bodies. For example, consider a gymnast holding the iron cross position. They are not falling, so the net force on them is zero. They are also not rotating, so the net torque is also zero. To solve any problem involving a rigid object in equilibrium, you must apply both conditions. The sum of forces is zero, and the sum of torques is zero. Let us bring together the core principles for analyzing a rigid object in equilibrium. For an object to be stable and not accelerate, two distinct conditions must be met simultaneously. First is translational equilibrium, which means the vector sum of all external forces acting on the object must equal zero. This ensures the object's center of mass does not accelerate. The second condition is rotational equilibrium, which requires the vector sum of all external torques about any axis to also be zero, ensuring the object has no angular acceleration. A common and important special case is called static equilibrium. This is when the object is completely at rest, meaning both its translational velocity and its angular velocity are zero. For the many problems where all forces lie in a single two-dimensional plane, these vector conditions simplify into three powerful scalar equations. The sum of the x components of the forces is zero, the sum of the y components of the forces is zero, and the sum of the torques is zero. These three equations are the essential tools for solving 2D static equilibrium problems. Let us use these two review questions to solidify our understanding of the conditions for equilibrium. First, consider an object with three forces whose lines of action pass through a common point. If we choose that point as our axis of rotation, the lever arm for each force is zero. This means the net torque is guaranteed to be zero, so the object is in rotational equilibrium. For the object to be in translational equilibrium, the vector sum of the forces must also equal zero, which is possible but not required by this setup. Next, think about the flywheel spinning at a constant rate. A constant angular velocity means the angular acceleration is zero. This implies the net torque is zero, so the flywheel is in rotational equilibrium. Since its center of mass is not accelerating, the net force is also zero, meaning it is in translational equilibrium as well. This is a great example of an object in equilibrium that is not in static equilibrium, because it is still moving. The key idea is that equilibrium requires zero net force and zero net torque, which means zero acceleration, not necessarily zero motion.